All right, let's jump right in. We're going to tackle a really fundamental challenge today. How in the world do you measure something you can't even see, like radiation? You know, it's a huge deal for things like medicine and science, and the answer? Well, it's actually pretty cool and surprisingly simple.
So yeah, that's the big question, right? How can you possibly put a hard number on a beam of energy that's completely invisible? It sounds like it should be impossible, but it turns out the solution is, well, beautiful in its simplicity, and it all comes down to some really basic physics.
Okay, so before we dive into how we measure it, we got to be clear on what we're measuring. The magic term here is absorbed dose. You'll often see it just as a capital D. And really, it's just what it sounds like, the amount of energy from radiation that gets soaked up by a certain amount of stuff, a certain mass. The sponge analogy is perfect. Think of it like that. We're just measuring how much energy water a material has soaked up.
All right, so how do we connect the dots here? You've got this invisible energy, and you want a number you can actually read. The secret, the fundamental link, is something we all experience every day: heat. It's all about turning that radiation energy into heat.
So here's the basic idea, and it's super straightforward. When radiation hits something and gets absorbed, that energy can't just disappear, right? It has to go somewhere. And what it does is it makes the molecules in that material start vibrating like crazy. And that vibration, well, that's just heat. So more radiation means more vibration, which means a higher temperature. This simple connection, that's the key to the whole thing.
And this leads to something really elegant. Remember how absorbed dose is energy per unit mass? Well, because of that, the mass part of the big equation actually cancels itself out. So we're left with this super simple formula you see here. The absorbed dose, or D, is just the material's specific heat capacity times the change in its temperature. And that is a huge deal. It means if we can just measure that tiny temperature change with enough precision, we can figure out the exact radiation dose. It's that direct.
Okay, so in theory, this sounds easy, right? Just measure a temperature change. But here's the catch. We are talking about ridiculously small changes in temperature. So what kind of crazy sensitive gadget can actually pull this off? Well, to find out, we have to look inside the machine itself.
And here it is. This is the device that makes it all happen, the calorimeter. Now, I know this diagram looks a little intimidating, but its job is actually super simple. The best way to think about it is like the most advanced thermos bottle you've ever seen. It's built to do just one thing and do it perfectly. Trap every last bit of heat generated by the radiation and measure it without any noise from the outside world getting in.
So how does this thing actually work? Well, it's pretty logical. First, the radiation beam zips into a vacuum chamber. That's so air or anything else doesn't mess with it. Then bam, it hits the heart of the calorimeter, this thing called the absorber. This is where all that energy gets dumped, and that, of course, makes it heat up just a tiny, tiny bit. And that's where this ultra-sensitive thermometer, a thermistor, comes in. It detects that minuscule temperature change and turns it into an electrical signal that we can actually read and analyze.
All right, so the machine did its part. We've got our temperature reading. Now for the fun part, turning that raw data into the actual dose. Let's do the math. And this brings us right back to where we started, to that beautiful, simple formula. You literally just take the temperature rise that the machine measured, plug it into the equation, multiply it by the specific heat of the absorber, which we already know, and boom, just like that, you have your number. A direct, absolute measurement of the absorbed dose. No guesswork.
It almost sounds too easy, doesn't it? A straight shot from temperature to dose. But in the real world, is anything ever that simple? As you've probably guessed, to get the kind of accuracy you need for, say, cancer treatment, there's a little more to the story.
Yeah, it's not quite that simple. To get that last fraction of a percent of accuracy, you have to account for a few little things. For one, a tiny bit of heat might still leak out, even from our superthermos. The radiation can also trigger some tiny chemical reactions that either add or subtract a little heat. And sometimes, really high-energy radiation might just punch right through without stopping. So scientists have to carefully calculate all these little effects and apply corrections to get that final super-duper precise number. Okay, so with all that said, the simple principle and the complex corrections, what's the final verdict? What's the bottom line on this whole calorimetry thing? Let's check out the report card for this amazing piece of tech.
The pros and cons are pretty clear-cut. On the plus side, the benefits are huge. This method gives you a direct, absolute measurement, which means you get insane accuracy. But there's a flip side. The setup is a real beast, super complex, and it's all built to measure these incredibly tiny temperature shifts. And like we just talked about, you need those careful corrections to really nail it.
But out of all the pros, this one is the big one.
The calorimeter is what's called a primary standard. Now, what does that mean? It means it's not just one way to measure radiation, it is the way. It's the ultimate benchmark. It's the master ruler that every other radiation detector in the world gets calibrated against. Basically, when it comes to measuring dose, the calorimeter is the final word, the source of truth.
And it's not like there's just one kind of calorimeter. It's not a one-size-fits-all kind of deal. You can use different materials inside as the absorber, depending on what you're trying to do. Graphite is a pretty common choice, good all-around standard. But for medical stuff, this is really cool. They use a water calorimeter. Why? Because our bodies are mostly water, so it gives you a measurement that's incredibly relevant for figuring out the exact dose for treating a patient.
So at the end of the day, why does any of this tech-heavy stuff matter? We've gone through all the physics and the engineering just to get one little number. But it's not just for a textbook. That primary standard level of accuracy, that's what lets a doctor aim a radiation beam to destroy a tumor while leaving healthy cells right next to it alone. It's what makes sure new therapies are safe and that they actually work. It's this quiet, unsung hero in the background of modern medicine. And it really makes you think, with this incredible level of precision, what other doors are we about to unlock?